Since its discovery in 1846, Neptune has remained one of the least understood planets in the solar system. Found through mathematics before it was ever seen through a telescope, the distant ice giant spends most of its existence as a tiny blue disk nearly 4.5 billion kilometers from Earth. For more than a century, astronomers could observe little more than its presence. Humanity's only close encounter came in 1989, when Voyager 2 revealed a surprisingly active world of violent storms, powerful winds, and unexpected atmospheric dynamics. Today, the James Webb Space Telescope is transforming that picture once again. Rather than a stable, predictable planet, Neptune appears to be changing in ways scientists struggle to explain. Its upper atmosphere has cooled dramatically since Voyager's measurements. Cloud systems have vanished and reappeared on unexpected timescales. Long-sought auroras have finally been detected in unusual locations. Each discovery challenges existing models. Together, they reveal a planet that remains one of the most dynamic and mysterious worlds in the solar system. The planet that defied its own seasons. Before JWST ever pointed at Neptune, the planet was already presenting a puzzle that no existing instrument could resolve. In April 2022, a team led by Dr. Michael Roman at the University of Leicester published a study in the Planetary Science Journal that synthesized 17 years of thermal infrared observations of Neptune gathered from some of the most powerful telescopes on Earth, including the European Southern Observatory's Very Large Telescope in Chile, the Gemini South and Gemini North telescopes in Chile and Hawaii, Hawaii's Subaru Telescope and Keck Telescope, and archival data from NASA's retired Spitzer Space Telescope. The synthesis was a significant undertaking, coordinating observations from multiple facilities over nearly 2 decades, each using slightly different instruments and calibration procedures, and reducing them to a coherent time series of stratospheric temperature measurements across Neptune's disk. The result was the most complete picture of Neptune's thermal evolution since Voyager 2. What the study found was this: between 2003 and 2018, the globally average temperature of Neptune's stratosphere, the atmospheric layer sitting above the active weather zone, dropped by approximately 8 degrees Celsius. On a planet whose stratospheric temperatures hover around -200 to 20 degrees Celsius, 8 degrees represents a significant fractional change in the thermal energy of the layer. The stratosphere is not the visible cloud layer. It sits above the region where Neptune's enormous storms form, and where the methane ice clouds that give the planet its appearance in visible light are located. The stratosphere is heated primarily by absorption of solar ultraviolet radiation, by methane and its chemical breakdown products, and it cools primarily by infrared radiation from those same products. Its temperature is a measure of the balance between these two processes. When something shifts that balance, the stratospheric temperature shifts with it. And between 2003 and 2018, something shifted it toward cooling, not warming, during the planet's southern summer. The timing was the core of the puzzle. Neptune's southern hemisphere had been in summer since 2005. Its southern summer solstice occurred that year, meaning the South Pole was tipped toward the Sun and receiving the maximum annual solar energy available to it. On any planet with a reasonably simple atmosphere, this increased solar energy input to the summer hemisphere should drive a stratospheric warming. The models built from basic atmospheric physics predicted that Neptune's southern stratosphere would warm during this period. Instead, it cooled by 8 degrees over 15 years. This was not a small discrepancy between model and observation. It was the model predicting one direction and the planet going the other. The cooling during summer was not the only surprise in the dataset. The same observational record revealed that as the global stratospheric temperature dropped, the South Pole itself briefly spiked warmer. An area near the geographic South Pole, the region receiving the most direct solar illumination during southern summer and therefore most expected to show warming, showed a temperature increase of roughly 11 degrees Celsius that stands out sharply against the surrounding atmospheric cooling. This polar spike was captured in thermal infrared images from 2018 and 2020, and was real in the sense of being independently detected by multiple instruments. Polar warming in summer is expected and predicted by basic seasonal models. A simultaneous global stratospheric cooling during that same summer is not. The two trends occurring together at the same time on the same planet, cooling globally and warming locally at the pole, pointed toward an atmospheric energy balance that existing models were not capturing. Roman's team proposed several possible explanations for the unexpected cooling pattern. Seasonal changes in atmospheric chemistry could alter how efficiently the stratosphere radiates heat away, potentially causing cooling through changes in the concentrations of photochemically produced hydrocarbon molecules that act as atmospheric coolants. If the production rate of certain radiating species changes over a Neptunian season, the stratospheric cooling rate could change too, producing the observed temperature shift, even if the solar energy input is increasing exactly as expected. A second possibility, tentative but noted in the paper, was some correlation between the 11-year solar cycle and Neptune's temperature evolution. The team was careful to describe this as suggestive rather than confirmed, and the data covering only about 1.5 solar cycles was insufficient to establish a periodicity with statistical confidence. But the solar cycle connection was inherently puzzling. Neptune sits 30 times farther from the Sun than Earth. The solar energy it receives is roughly 900 times weaker than what Earth receives. Attributing meaningful temperature changes to the solar cycle required explaining how such a faint signal at such a vast distance could produce measurable effects in a planetary stratosphere. The 2022 study did not resolve these questions. That was not its purpose. It was the paper that defined the questions sharply enough and with sufficient observational support that JWST could begin to address them systematically. Roman's team stated explicitly that JWST, with its infrared sensitivity far exceeding any previous space telescope and its spectroscopic capability for directly measuring molecular abundances and temperatures in Neptune's atmosphere, was the instrument that might finally distinguish between the competing explanations. What JWST found when it looked at Neptune confirmed the cooling and added an entirely new layer of strangeness on top of it, suggesting that the 2022 study had identified only the surface of a problem that goes considerably deeper. Why JWST sees Neptune differently than every previous telescope. Every image of Neptune captured before JWST was taken primarily in visible light. Voyager 2's cameras operated in visible wavelengths. The Hubble Space Telescope's iconic blue Neptune images were captured in visible wavelengths. The ground-based telescopes that tracked Neptune's weather patterns for decades operated primarily in visible light, with some near-infrared capability added to later instruments in the 2000s and 2010s. Ground-based adaptive optics systems on the Keck and Gemini telescopes provided some infrared imaging capability, but Earth's own atmosphere absorbs significant fractions of the near-infrared spectrum before it reaches even the best ground-based detectors, limiting both sensitivity and wavelength coverage. JWST does not work in visible light at all. Its primary scientific instruments, the near-infrared camera known as NIR-CAM, the near-infrared spectrograph known as NIR-SPEC, the near-infrared imager and slitless spectrograph known as NIR-ISS, and the mid-infrared instrument, known as MIRI, operate in wavelengths between approximately 0.6 and 28 micrometers. Human vision covers roughly 0.4 to 0.7 micrometers. JWST's full range extends from just at the edge of visible red light, where human eyes are already losing sensitivity, to wavelengths nearly 40 times longer than the longest wavelength visible light. This puts the telescope in a completely different observational regime from every instrument that had previously characterized Neptune's atmosphere, rings, and moons. This matters for Neptune in a way that is specific to the planet's chemistry. Neptune's atmosphere contains approximately 1 to 2% methane by volume, a fraction that sounds small but dominates how the planet interacts with light across a wide range of wavelengths. At visible wavelengths, methane absorbs red light efficiently and scatters blue light back outward. This is why Neptune appears its characteristic rich, saturated blue to any visible light telescope, richer and more deeply blue even than Uranus, despite the two planets having similar methane fractions, a difference attributed to Neptune's smaller amounts of high-altitude haze that would otherwise dilute the methane absorption signal. The blue colour is beautiful and immediately recognisable, but it is not very informative. The methane is telling you very little about the atmosphere below it when observed at visible wavelengths, because most of the visible light you detect is being reflected from the upper atmosphere where the methane absorbs and scatters it. Deeper layers are effectively hidden. At near-infrared wavelengths, methane absorbs so strongly that the planet itself appears almost dark. This is not a subtle effect. When NIR-CAM images Neptune at wavelengths between 2 and 5 micrometers, the methane in Neptune's atmosphere absorbs nearly all the light that tries to pass through it in both directions, inward and outward. The planet's disk becomes a deep, nearly featureless dark sphere. The light that would normally reflect off Neptune's atmospheric layers and clouds at multiple depths is absorbed by methane before it can return to JWST's detectors. What was Neptune's most recognizable feature, its vivid blue color, vanishes entirely in JWST's infrared images. You are not looking at a blue planet. You are looking at a dark one. This infrared darkness of Neptune's lower and middle atmosphere is paradoxically what makes JWST such a powerful Neptune observatory. Because the background planetary disk becomes very dark in infrared, anything that rises above the primary methane absorption layer stands out against it, with extreme contrast. High-altitude methane ice clouds, which form where temperatures are cold enough for methane gas to freeze into ice crystals at altitudes above the main methane gas column, reflect sunlight before that light has had to pass through most of the absorbing methane. These clouds appear as brilliant white or bright features against the otherwise dark disk. In Hubble visible light images, these same clouds appear as slightly brighter features against an already bright blue background. In JWST's infrared images, they become the dominant visible structures on the planet, standing out dramatically against the dark disk. Features that were subtle and difficult to characterize in visible light become obvious and precisely measurable in infrared. Ring material that is too faint to detect against the bright visible planet becomes detectable against the dark infrared disk. Atmospheric features at different altitudes invisible in visible light because they produce only subtle color variations in a uniformly blue planet become detectable in infrared because they have different temperatures and emit different amounts of thermal radiation that JWST can measure. The near-infrared spectrograph adds a further dimension that no previous telescope could provide. NIR-SPEC disperses the light from Neptune into a detailed spectrum measuring the intensity at thousands of individual wavelengths simultaneously. Each molecule in Neptune's atmosphere has a characteristic pattern of emission and absorption at specific wavelengths, a spectroscopic fingerprint as unique as a physical one. By measuring the spectrum with sufficient sensitivity and resolution, NIR-SPEC can identify which molecules are present in the atmosphere, measure their concentrations at different altitudes, and determine the temperature of the atmospheric layers they occupy from the shape of their spectral emission features. It is this capability that detected the H3+ aurora emission and measured the ionospheric temperature that represented the most dramatic single JWST finding about Neptune, the factor of 2 cooling since Voyager 2, the rings that came back from the dead. When NASA released the first JWST image of Neptune on September 21, 2022, the scientific community's reaction was immediate and in some quarters deeply emotional. Heidi Hammel, a planetary scientist who had been part of the original Voyager 2 imaging team in 1989, and who serves as a Webb interdisciplinary scientist with responsibility for solar system observations, stated that she cried when she saw the image. She had waited 33 years to see Neptune's rings this clearly again. The cause of that reaction was not merely the planet itself, but what surrounded it. A ring system that had been essentially invisible to any instrument for more than 3 decades, rendered suddenly strikingly clear. Neptune has 5 named rings. From innermost to outermost, they are the Galle ring, the Leverrier ring, the Lassell ring, the Arago ring, and the Adams ring, all named after figures connected to the planet's discovery. They were suspected before Voyager 2's 1989 flyby, based on occultation observations in which astronomers timed the dimming of a background star as Neptune passed in front of it. Careful analysis of these timings revealed brief additional dips in the star's brightness that suggested ring material near the planet. The detections were puzzling because they were inconsistent. Sometimes the dips appeared symmetrically on both sides of the planet, suggesting complete rings that extended all the way around, and sometimes they appeared on only one side, suggesting incomplete ring arcs rather than full rings. The debate about whether Neptune had complete rings or only disconnected arcs was unresolved until Voyager 2 settled it definitively by photographing the full ring system directly during its 1989 flyby. After Voyager 2, ground-based telescopes struggled to image the rings directly. The rings are faint, and Neptune's bright visible light disk creates an overwhelming glare that makes detection of ring material close to the planet extremely difficult, even with sophisticated scattered light suppression techniques. The denser parts of the Adams ring, particularly its well-known clumped arcs of higher material density, could occasionally be detected with the largest ground-based telescopes equipped with adaptive optic systems under excellent atmospheric conditions. But these detections were difficult and required significant effort. The fainter rings, including the Galle ring's broad, diffuse material, spread across a wide radial range, and the dusty bands between the main rings that Voyager had imaged were essentially invisible from the ground. For more than 30 years after Voyager, the complete picture of Neptune's ring system that the flyby had provided in 1989 existed only in those original Voyager images and the data archive they generated. The JWST NIR CAM image changed this in a single exposure. All 5 rings appeared with a clarity that had not been seen since Voyager. The narrow, well-defined rings, particularly the Leverrier ring and the Adams ring, show up as crisp, bright arcs around the dark planetary disk with details sufficient to identify structural features within them. The faint dust bands, which had not been successfully imaged since Voyager 2's cameras captured them in 1989, reappear clearly in the gaps between the main rings, their faint luminosity visible against the dark infrared background, in a way that would have been impossible to extract from their faint signal against a bright visible light disk. The Galle ring, the innermost and most diffuse of the 5 rings, appears as a broad, soft glow surrounding the inner ring system, its extent and structure visible for the first time since 1989. The scientific significance of the JWST ring image extends well beyond its visual impact. As Hamill noted in the press release accompanying the image, it had been 3 decades since the dusty rings were last seen, and this was the first time they had been seen in the infrared. That final phrase is the scientifically important one. Every prior detection of Neptune's rings, from Voyager 2 through the occasional ground-based visible detection of the brightest Adams ring features, was made at visible wavelengths. The JWST image represents the first infrared detection of the complete ring system. This matters because infrared wavelengths interact with ring material differently than visible wavelengths, depending on the particle size, composition, and optical depth of the ring material. Large particles and small particles scatter and absorb light in wavelength-dependent ways that produce different brightness profiles across the spectrum. By comparing how bright each ring component appears in JWST's infrared data relative to how it appeared in Voyager's visible data from 1989, scientists can constrain the physical properties of the ring particles in ways that single wavelength observations cannot accomplish. The dust bands in particular carry information about the very smallest particle populations in the ring system, particles that are most sensitive to non-gravitational forces like radiation pressure and electromagnetic effects. Their infrared brightness profile constrains the balance between these forces and the gravitational dynamics that determine where dust collects and how long it survives in the ring environment. The brightness that should not be where it is. The JWST CAM image of Neptune contains several brightness features within the planetary disk itself that were not predicted by existing models and whose physical interpretation planetary scientists are still actively working through. Understanding these features requires thinking about what determines the brightness of different parts of a planet in infrared observations, which is fundamentally about temperature and about where in the atmosphere light is originating. In visible wavelengths, the brightness of different locations on Neptune's disk is determined primarily by how much sunlight is reflected from the cloud and haze layers. Brighter regions are more reflective, darker regions less so. In near-infrared wavelengths, the situation is more complex. The dark methane absorption that makes the planet's disk appear dark at these wavelengths means that the brightness of any given location on the disk is determined by which altitude levels are contributing light that can escape the atmosphere without being absorbed by methane. High-altitude features, those that sit above most of the methane column, can reflect sunlight outward before that light has to pass through the absorbing gas. Low-altitude features, whether they are cloud structures or temperature anomalies, are hidden behind the methane curtain. What JWST sees in its infrared images is therefore primarily a map of the high-altitude atmospheric properties of Neptune, sensitive to features at altitudes that visible light telescopes cannot easily access. The most prominent brightness features in the 2022 NIR-CAM image of Neptune's disk are the high-altitude methane ice clouds. These appear as dazzling white patches and streaks, distributed primarily at mid-latitudes of the planet, standing out against the very dark infrared background, with a contrast that makes them far more visually striking than they ever appeared in visible light images where the bright blue background diluted their signal. Previous observations with Hubble and ground-based telescopes had detected methane ice clouds on Neptune at visible wavelengths, particularly after the Keck Observatory's adaptive optic systems became capable of resolving them. But the JWST infrared image captures them with a fidelity and contrast that reveals their structure in new detail, and the specific near-infrared wavelengths at which they appear allows estimates of their altitude, because different wavelengths probe different depths of the methane absorption layer. More subtly and more scientifically intriguing, the image shows a thin, bright band encircling the planet at approximately the equatorial latitude. The NASA press release describing the image identified this equatorial band as potentially representing a visual signature of the global atmospheric circulation that powers Neptune's wind system. The proposed mechanism is rooted in the dynamics of Neptune's atmospheric circulation. At the equator, models of ice giant atmospheric circulation predict that air descends from higher altitudes toward lower altitudes, compressing adiabatically as it does so. When a gas is compressed without exchanging heat with its surroundings, it warms. This adiabatic warming of descending equatorial air would create a temperature structure at the equator that is slightly elevated relative to the surrounding latitudes at the same altitude. A slightly warmer equatorial atmosphere emits slightly more thermal infrared radiation than cooler surrounding regions, producing the equatorial brightening visible in the image. If this interpretation is correct, the thin, bright equatorial band is a direct infrared image of the downward branch of Neptune's global atmospheric circulation cell, the cell whose upward branch drives convection that interacts with the planet's rotation through the Coriolis effect to produce the extreme retrograde equatorial winds of more than 2,100 kilometers per hour. This would make the JWST image the first direct observational visualization of the driving mechanism of Neptune's most extreme atmospheric feature. The brightening at the northern polar region, described in NASA's press release as hinting at an intriguing brightness, is the other notable disk feature that existing models do not fully explain. Neptune's north pole has been coming into better visibility from Earth as the planet progresses in its 165-year orbit, and in 2022 it was visible but not yet fully face-on. The brightening there could represent a thermal anomaly, with the North Polar region warmer than surrounding latitudes for reasons that are not obvious given that the South Pole is currently receiving more direct solar illumination. It could alternatively represent a polar atmospheric vortex, a coherent rotating feature similar to the polar vortices known from other giant planets, that concentrates high-altitude material over the pole and makes it reflective. Distinguishing between these possibilities requires spectroscopic temperature mapping of the polar region, which NIR-SPEC can provide by measuring the atmospheric temperature from the shapes of molecular emission lines at different latitudes simultaneously. These follow-up observations were obtained in the same June 2023 campaign that detected the aurora and measured the ionospheric temperature, and their analysis is contributing to a more complete three-dimensional thermal model of Neptune's atmosphere than any previous dataset could support. The cloud disappearance. In August 2023, a team led by Erandi Chavez at the Harvard-Smithsonian Center for Astrophysics published a study in the journal Icarus documenting one of the most striking observations in recent Neptune science. The planet's methane ice clouds had almost entirely disappeared. The Keck Observatory in Hawaii and the Hubble Space Telescope both contributed data to the study, and the combined dataset from the two facilities established the timeline of the cloud disappearance with a clarity that a single facility could not have achieved. The findings were published the same week as Heidi Hammel presented the initial JWST Neptune cloud monitoring results at a planetary science conference, creating a moment when the two independent lines of observation converged on the same anomalous finding from different directions. Neptune's methane ice clouds had been observed continuously and consistently since the early 1990s. Hubble images from throughout the 1990s and 2000s showed a planet with active cloud patterns at multiple latitudes, organized in the kind of bright streaks and patches that planetary scientists recognized as consistent with convective updrafts carrying methane gas to altitudes cold enough for condensation. Keck Observatory images, which became available with full adaptive optics capability in the late 1990s and early 2000s, provided higher spatial resolution views that revealed the detailed structure of these cloud features, their evolution from orbit to orbit, and the way they organized into latitudinal bands associated with Neptune's wind system. The Keck dataset in particular built up a rich 30-year archive of Neptune's near-infrared cloud morphology that became the basis for most of what planetary scientists understood about the planet's atmospheric dynamics. Beginning in late 2019, the clouds began to vanish. The change was gradual at first, with cloud coverage appearing reduced in 2020 compared to the historical baseline. By 2021, the reduction was more dramatic. Images from 2022 showed a Neptune that, outside of a persistent feature near the South Pole that had been present for decades and appeared to represent a stable meteorological feature anchored to the South Polar vortex, was essentially featureless in the cloud-forming altitude range. In nearly 30 years of continuous near-infrared monitoring by Keck and Hubble, Neptune's cloud coverage had never come close to this level of suppression. The planet had been transformed from a dynamically active, cloud-decorated world to something that appeared almost quiescent at the altitudes where previous images had always shown activity. The cloud disappearance is scientifically significant for multiple reasons that extend beyond the visual impression. Methane ice clouds on Neptune form when convective updrafts in the atmosphere carry methane gas from warmer, lower atmospheric layers to colder, higher ones. When the gas reaches altitudes where the temperature drops below the freezing point of methane under the local pressure conditions, it condenses into ice crystals. The altitude at which this condensation occurs depends on both the temperature profile of the atmosphere and the abundance of condensation nuclei, tiny aerosol particles on whose surfaces ice crystals preferentially form. Without sufficient condensation nuclei, even methane-saturated air at the right temperature may not readily form clouds. The cloud disappearance could therefore reflect either a change in the temperature profile of Neptune's middle atmosphere that has shifted the condensation level to altitudes where observations cannot detect it, or a reduction in the abundance of condensation nuclei that has made cloud formation less efficient even when the thermodynamic conditions are otherwise favorable. Chavez's team proposed that the disappearance was connected to the 11-year solar cycle through the aerosol mechanism. Ultraviolet radiation from the Sun drives photochemical reactions in Neptune's upper stratosphere that produce complex hydrocarbon aerosol particles. These aerosols gradually settle downward through the atmosphere and, at the right altitudes, serve as the condensation nuclei on which methane ice forms. When solar UV flux increases during the active phase of the solar cycle, aerosol production increases. More condensation nuclei are available at cloud-forming altitudes, and cloud coverage is enhanced. When solar UV flux decreases during the solar minimum, aerosol production drops, condensation nuclei become scarcer, and cloud formation is suppressed. With a lag of approximately 2 years between the solar UV change and the observable cloud response, reflecting the time needed for photochemical reactions to process the UV change into altered aerosol production, and for that altered production to propagate through the atmospheric layers to cloud-forming altitudes. The timing of the disappearance beginning in late 2019 and 2020 coincided with the solar minimum between solar cycles 24 and 25. The atmospheric temperature drop that makes no sense. The Roman et al.'s 2022 study established that Neptune's stratosphere had cooled by approximately 8 degrees Celsius between 2003 and 2018, while the planet was entering and progressing through southern summer. This was anomalous because seasonal models predicted warming, and the observed cooling was in the opposite direction. It was the clearest single demonstration that the theoretical framework for understanding Neptune's atmospheric energy balance was missing something important. But what JWST found when it measured Neptune's upper atmosphere in 2023 was more extreme than the stratospheric cooling by a factor that required a different level of explanation. The Roman et al. Finding concerned the stratosphere, the atmospheric layer extending from roughly 50 to 300 kilometers altitude above Neptune's visible cloud deck, where temperatures are set by the balance between solar UV absorption and infrared emission from hydrocarbon photochemical products. The JWST finding concerned the ionosphere, the uppermost layer of the atmosphere at altitudes above roughly 1,000 kilometers, where the gas is so thin that individual molecules can travel long distances without colliding, and where the thermal state is set by a completely different set of physical processes. In the ionosphere, heating comes primarily from absorption of the sun's extreme ultraviolet radiation and from the energy deposited by charged particles that enter the atmosphere along magnetic field lines during auroral events. Cooling is dominated by infrared emission from molecular ions, particularly H3+, which radiates efficiently at the wavelengths JWST observes. The 2025 Nature Astronomy paper by Mellon and colleagues, which is discussed in more detail in Part 2 in the context of the aurora discovery, contained the ionospheric temperature measurement derived from the H3+ spectral emission detected by NIR spec in June 2023. The temperature of the ionosphere extracted from the relative intensities of different H3 plus emission lines, was 358 Kelvin, approximately 85 degrees Celsius. When Voyager 2's ultraviolet spectrometer measured the same layer in 1989 using a different technique based on the refraction of sunlight as Voyager passed behind Neptune, the value was approximately 750 Kelvin. The difference between these two measurements is 392 Kelvin. The ionosphere has lost more than half of its thermal energy in the 34 years between Voyager 2 and JWST. The physical significance of a factor of 2 reduction in ionospheric temperature is difficult to overstate. Temperature in the ionosphere is not simply a number that varies slightly with orbital season or solar activity. It is a direct expression of the energy balance between the processes that heat the gas and the processes that cool it. If the temperature has halved, the total thermal energy content of the ionosphere has halved. Something has either dramatically reduced the heating rate, dramatically increased the cooling rate, or both, in a sustained way that has persisted for at least the 34 years between the two measurements. Lead author Henrik Mallin's statement in the press release was pointed and chosen with precision. I was astonished. Neptune's upper atmosphere has cooled by several hundreds of degrees. In fact, the temperature in 2023 was just over half of that in 1989. Mallin's astonishment was not a rhetorical flourish. It reflected a genuine disconnect between the measurement and everything the existing theoretical framework predicted. The solar cycle does not readily explain this, while the sun's extreme ultraviolet output varies by perhaps 20 to 30% between solar maximum and solar minimum. This variation is not enough to halve the ionospheric temperature. A 20 to 30% variation in the heating rate would produce at most a comparable fractional change in equilibrium temperature if all other factors remain constant, and the actual temperature change is not 20 to 30%, but roughly 52%. Furthermore, the June 2023 observation that produced the JWST temperature measurement was made during solar cycle 25's rising phase, rather than during a deep solar minimum, making reduced solar UV an implausible first-order explanation, even setting aside the magnitude problem. The Sun was becoming more active at the time of the measurement, not less, which if anything should have been driving the ionospheric temperature toward higher values rather than the low value detected. Enhanced H3 plus cooling is a physically possible alternative mechanism. H3 plus is an efficient infrared coolant, and if its abundance in Neptune's ionosphere had significantly increased between 1989 and 2023, the cooling rate would have increased correspondingly. But increased H3 plus abundance would itself require explanation. H3 plus forms when energetic particle precipitation from auroral processes ionizes molecular hydrogen, and a sustained increase in H3 plus abundance would imply a sustained increase in auroral particle input to the ionosphere. This increased auroral activity would itself be expected to produce increased heating from the particle energy deposited in the upper atmosphere, partly offsetting the increased H3 plus cooling. Achieving a net cooling of the magnitude observed through this mechanism alone would require a specific and unusual combination of circumstances. A third possibility is that the 1989 Voyager 2 measurement was made during an unusually warm phase of Neptune's ionospheric temperature cycle, and that the 2023 JWST value is closer to the typical long-term average. If Neptune's ionosphere cycles between warm and cool states on timescales of years to decades, driven by some periodic or quasi-periodic process not yet identified, then two measurements separated by 34 years might simply have sampled the system at different phases of this cycle. Testing this hypothesis requires a temporal baseline of observations covering multiple cycles, which JWST is now positioned to begin building. The paper's authors called explicitly for continued observations to track the temperature's evolution, because without knowing whether the 358 Kelvin value is stable, still declining, or beginning to recover toward the Voyager value, it is impossible to identify the mechanism responsible. Each possible trajectory implies a different physical cause, and only the time series that JWST can now accumulate will discriminate among them. What the comparison between 1989 and 2023 has established beyond doubt is that Neptune's ionosphere is capable of dramatic changes on the timescales of a human scientific career, and that the theoretical framework that existed before JWST was insufficient to predict or explain those changes. The dark vortex that changed its mind. Neptune's dark vortex storms are the most dramatic large-scale weather features on the planet, and among the most distinctive atmospheric phenomena in the outer solar system, and JWST's continued monitoring of Neptune's disk is contributing new information about their behaviour at infrared wavelengths that no previous instrument was positioned to provide. Understanding what makes these storms scientifically important requires first establishing what makes them unusual compared to analogous storm systems on other giant planets, and why their behaviour continues to confound the models built to explain them. The first large dark vortex observed on Neptune was the Great Dark Spot detected by Voyager 2 in August 1989. It was an oval-shaped dark feature in Neptune's southern hemisphere with a long axis comparable to Earth's diameter, embedded in a region of extreme wind shear, where eastward and westward wind bands met at the latitude of the storm. Along the boundaries of the vortex, wind speeds were measured at up to 2,400 kilometers per hour, among the highest ever recorded in any planetary atmosphere. Companion clouds of methane ice, bright against the blue Neptunian background, formed in the vortex's vicinity as atmospheric flow was forced upward around its edges to altitudes cold enough for methane condensation. The system was visually striking and dynamically impressive, clearly one of the most energetic weather systems anywhere in the solar system. When Hubble turned toward Neptune in 1994, 5 years after the Voyager flyby, the Great Dark Spot had vanished completely. Not faded, not weakened, gone. No trace remained of a storm that had appeared comparable in scale to Earth itself. This was immediately and obviously anomalous by comparison with Jupiter. The Great Red Spot on Jupiter has been documented for at least 350 years, and while it has been measurably shrinking in recent decades, it shows no sign of imminent dissolution. Neptune's Great Dark Spot, by apparent contrast, had existed for years rather than centuries. Hubble subsequently detected a new large dark vortex in Neptune's northern hemisphere, and over the following decades, several more were observed to appear, evolve, and dissipate on timescales measured in years. The pattern established a fundamental distinction between Neptune and Jupiter. Neptune's major vortex storms are transient on human timescales, while Jupiter's are essentially permanent on any timescale short of centuries. The vortex observed by Hubble beginning in 2018 was the most extensively tracked of the series detected since 1994. Unlike some of the earlier detections, which were observed only briefly before becoming undetectable, the 2018 vortex remained visible for multiple years, allowing its evolution to be followed in detail. Initial tracking showed the vortex drifting southward toward Neptune's equator. On every prior occasion that a Neptune dark vortex had been tracked approaching the equatorial region, it had dissipated as it entered the zone of different wind regime. Models suggested that the equatorial wind shear was inhospitable to the vortex structure, essentially tearing it apart when it moved too far from the mid-latitude environment where it had formed and been sustained. The 2018 vortex appeared to be following this familiar trajectory toward dissolution. In 2020, images from Hubble showed that the storm had reversed direction and was heading northward. This reversal was unprecedented in the observational record and was not predicted by any existing vortex model. Simultaneously, The companion clouds that had been associated with the vortex, the bright methane ice features that formed in the elevated flow around the storm's edges, disappeared. Their absence was separately anomalous. Companion clouds had been detected around dark vortices as consistent features in every previous case where the observational conditions allowed their detection. JWST's infrared observations of Neptune contribute to understanding this kind of event by providing thermal structure information at the vortex altitudes that visible light images cannot access. A vortex that appears dark in visible light because it exposes lower atmospheric layers may appear thermally distinct in infrared because those lower layers have different temperatures from the surrounding atmosphere. The interior of a dark vortex, if it is a region of upwelling that brings warmer gas from below to altitudes where it would not normally be found, would appear brighter in thermal infrared than the surrounding atmosphere. Alternatively, if the vortex interior is a region of anomalously cold gas trapped in a rotating column, it would appear darker in thermal emission than its surroundings. Distinguishing between these possibilities is not possible from visible light images alone, which measure reflected sunlight rather than thermal emission. JWST's MIRI instrument, operating at mid-infrared wavelengths where Neptune's thermal emission dominates over reflected sunlight, can map the temperature anomaly associated with a dark vortex directly, defining its three-dimensional thermal structure and constraining the dynamics that sustain it. The theoretical question of why Neptune's vortices are transient while Jupiter's are persistent remains incompletely answered. One proposed explanation involves the depth of the driving layer. Neptune's major atmospheric motions are driven primarily from below by interior convection rather than by solar heating from above. If the vortices draw their sustaining energy from the underlying convective layer, they may be inherently less stable than Jupiter's storms, which tap into a more organized latitudinal wind structure, maintained by a more regular atmospheric energy input. A second explanation focuses on Neptune's extreme wind shear. The retrograde equatorial winds and prograde polar winds produce a strong differential flow that could efficiently disrupt vortices that migrate into the shear zone, pulling at their edges and preventing the coherent rotation that sustains them. The reversal of the 2018 vortex as it approached the equatorial zone and the simultaneous disappearance of its companion clouds suggesting the dynamics maintaining the storm were changing before the reversal became apparent, are consistent with this shear disruption mechanism beginning to act. JWST's thermal mapping of vortex structures, combined with continued Hubble visible light tracking of vortex positions and companion cloud morphology, will provide the multi-wavelength dataset needed to evaluate which mechanisms are dominant in determining how long Neptune's planet-sized storms can persist. Triton in a new light. In the JWST image released in September 2022, the brightest object in the frame is not Neptune itself. It is Triton, Neptune's largest moon, appearing as a star-like point of light to the upper left of the planetary disk, with diffraction spikes radiating outward from it. The cross-shaped pattern that JWST's mirror design produces around bright point sources. The fact that a moon outshines the planet it orbits in JWST's infrared image is not simply a photographic curiosity. It reflects a genuine physical property of Triton's surface that makes it one of the most reflective objects in the solar system. And that same property is what makes Triton a target of intense scientific interest for JWST's spectroscopic follow-up program. Triton reflects approximately 70% of the sunlight that strikes it, an albedo that places it among the brightest natural objects in the solar system. By comparison, Earth's average albedo is about 30%, the Moon's is about 12%, and most rocky and icy bodies in the outer solar system fall in the range of 5 to 40%. Triton's unusually high reflectivity comes from its surface composition. The Moon is covered in ices of nitrogen and methane, that were deposited and refreshed by the geological activity that Voyager 2 detected in 1989. These fresh crystalline ices scatter light very efficiently across a broad wavelength range, making Triton bright, both in visible light and in the near-infrared wavelengths where JWST observes. Neptune's atmosphere, with its methane-absorbing infrared light, reflects comparatively little in JWST's wavelength range. The result is that the small, cold moon appears as the dominant bright object in the image, while the large, warm planet appears relatively dark. Triton is scientifically extraordinary in multiple respects, beginning with its orbit. Every other large moon in the solar system orbits in the prograde direction, the same direction as its planet's rotation, because moons form from the same spinning disk of material that formed their parent planets and inherited that rotation. Triton orbits in the retrograde direction opposite to Neptune's rotation at an inclination of approximately 157 degrees to Neptune's equatorial plane. This orbital configuration is the unmistakable signature of a captured object, a body that formed elsewhere in the solar system and was subsequently grabbed by Neptune's gravity. The leading theory is that Triton originated in the Kuiper belt, the vast reservoir of icy objects beyond Neptune's orbit, and that a gravitational interaction with Neptune, possibly involving a binary system in which Triton was paired with a smaller companion, resulted in Triton being captured while the companion was ejected. Over the billions of years since the capture, tidal interactions between Triton and Neptune have circularized what was originally an eccentric capture orbit into the nearly perfect circle Triton follows today, while the retrograde direction of the orbit has been preserved as a lasting record of Triton's foreign origin. The consequence of this retrograde orbit is that Triton is slowly spiraling inward toward Neptune. Tidal forces between a moon and its parent planet act differently depending on whether the moon's orbit is prograde or retrograde. For a prograde moon orbiting in the same direction as the planet rotates, the planet's tidal bulge, raised by the moon's gravity and carried slightly ahead of the moon by the planet's rotation, tugs the moon forward and adds energy to its orbit, causing it to spiral outward. For Triton, orbiting in the retrograde direction while Neptune still rotates prograde, the same tidal interaction removes energy from the orbit. Triton is losing orbital energy and spiraling inward at a rate that, sustained over the next 3.6 billion years, will bring it within Neptune's Roche limit, the distance inside which tidal forces exceed the gravitational self-attraction holding Triton together. At that point, Triton will be torn apart, and the material from its disruption will spread into a ring system around Neptune, potentially rivaling Saturn's in scale and visual splendor. The JWST spectroscopic program for Triton aims at characterizing the composition and spatial distribution of its surface ices in detail that Voyager 2's brief flyby could not achieve. Voyager 2 identified nitrogen ice as the primary surface constituent, with methane ice as a secondary component, and found evidence for complex organic compounds called tholins that give some regions of the surface a reddish tinge. JWST's NIR spec can detect all of these species and potentially additional ones, including carbon monoxide, carbon dioxide, and water ice if present, and can map their distributions across Triton's visible surface. This compositional mapping connects to the question of Triton's potential subsurface ocean, because material transported from a deep liquid reservoir to the surface by cryovolcanic processes would have a distinct composition from material deposited purely by condensation of atmospheric gases or by radiation chemistry operating on surface ice. The internal heat mystery gets sharper. Neptune emits significantly more energy as thermal radiation than it receives from the Sun. The thermal excess, the ratio of total emitted energy to absorbed solar energy, is approximately 2.6 for Neptune, meaning the planet radiates to space 2.6 times the energy it absorbs from sunlight. Every other large planet in the solar system, except Uranus, has a similar thermal excess, the consequence of retaining primordial heat from the planet's formation billions of years ago. When the solar system's giant planets accreted from the surrounding nebula, the gravitational energy of infalling material was converted to heat. This primordial heat has been radiating away ever since, and the fact that it is still detectable today, billions of years after formation, reflects how slowly heat escapes from the deep interiors of massive planets. Uranus is the striking exception, radiating almost exactly what it receives from the Sun, and appearing to have either lost its primordial heat almost entirely or locked it in a thermally stratified interior from which it cannot escape. Neptune's internal heat flux is not just a number, it is the energy source that drives the planet's extraordinary atmospheric dynamics. At Neptune's distance from the Sun, the solar energy received per unit area of the planet's surface is roughly 900 times less than at Earth. This amount of solar energy could drive only very gentle atmospheric motions by the standards of what is actually observed. The 2,100 kilometers per hour equatorial winds, the planet-sized vortex storms that appear and disappear within years, the complex latitudinal banding that organizes Neptune's atmospheric circulation into distinct zones and belts. None of these are solar-driven phenomena in any significant sense. They are driven by the heat flowing upward from the planet's interior, which convects through the atmospheric layers and, interacting with the Coriolis effect from the planet's rotation, organizes into the dynamics observed at the visible cloud top. JWST's thermal observations of Neptune contribute to measuring the internal heat flux with greater precision than was previously possible. The total thermal emission from the planet, measured by MIRI at mid-infrared wavelengths where planetary thermal emission is large relative to reflected sunlight, determines how much power the planet is radiating to space. Subtracting the calculated solar energy absorbed by the planet, based on Neptune's known albedo and distance from the Sun, gives the internal heat flux directly. Previous measurements of Neptune's thermal excess were based on Voyager 2 infrared data from 1989 and on ground-based observations affected by Earth's atmosphere. JWST's measurements from above Earth's atmosphere at infrared wavelengths where Earth's own atmosphere would otherwise cause significant absorption allow a more precise measurement that constrains the internal heat budget more tightly than before. This constraint matters for understanding what processes contribute to the internal heat. The most straightforward contribution is the slow cooling of primordial heat that has been present since formation. When Neptune formed, the gravitational energy of the colliding and infalling material that built the planet was converted to heat. The planet was initially very hot, perhaps hot enough to be partially molten throughout much of its volume, and it has been radiating that heat away ever since. The rate at which this cooling proceeds depends on how efficiently heat can be transported from the deep interior to the surface, which in turn depends on the planet's internal structure, the thermal conductivity of its constituent materials under the relevant pressure and temperature conditions, and whether convection or diffusion dominates the heat transport at different depths. For Neptune, the combination of these factors has allowed a significant internal heat reservoir to persist over the 4 billion years since formation, producing the 2.6-fold thermal excess still measurable today. But primordial heat retention may not be the only contributor to Neptune's thermal excess. Additional internal processes can release heat into the planet's interior on timescales relevant to the present. One of the most discussed is the gravitational differentiation of heavy elements toward the planetary center. If dense materials, including silicate minerals and metallic species, have been slowly sinking toward Neptune's core over geological time while lighter materials rise, the release of gravitational potential energy from this differentiation process generates heat that adds to the primordial budget. The magnitude of this contribution depends on how much differentiation has actually occurred versus how much remains to happen, parameters that are not directly observable but that can be constrained by comparing the measured internal heat flux with the predictions of interior evolution models. Diamond crystallization is another potential heat source that has received specific attention in the context of Neptune. Laboratory experiments published in the years before and after JWST's launch confirmed that under the temperature and pressure conditions expected in Neptune's mantle, carbon atoms liberated from methane molecules can crystallize into diamond. This crystallization process releases latent heat, the thermal energy associated with the phase transition from liquid or amorphous carbon to crystalline diamond. If diamond formation is actively occurring in Neptune's mantle today at a sufficient rate, the latent heat released could contribute measurably to the planet's total thermal output. Estimating this contribution requires knowing the rate of diamond crystallization, which depends on the chemical composition and thermodynamic state of the mantle, parameters accessible only through laboratory experiments at extreme conditions or through theoretical models. JWST's more precise thermal emission measurements, combined with an improved understanding of Neptune's atmospheric opacity at the mid-infrared wavelengths MIRI observes, allow the total internal heat flux to be determined with smaller uncertainty than before. This tighter observational constraint on the heat flux can then be compared with the sum of contributions predicted by different interior models. If the measured flux is consistent with primordial heat alone, differentiation and diamond crystallization are either minor contributors or have largely run their course. If the measured flux exceeds what primordial heat models predict, the additional contributions must be significant, and their magnitudes constrain the interior composition and evolution history. Each constraint of this type is a step toward a self-consistent model of Neptune's interior that can connect the observable thermal emission at the top of the atmosphere to the exotic physics occurring at pressures of millions of atmospheres deep inside the planet. Physics that cannot be directly sampled by any instrument ever built or currently planned. Neptune's magnetic field and the architecture of its mysteries. Every anomaly that JWST has identified in Neptune's observable atmosphere traces back, in one way or another, to the planet's interior. The stratospheric temperature drop connects to photochemistry that depends on solar UV and on the chemical environment set partly by material rising from the interior. The ionospheric temperature connects to auroral energy input that is controlled by the magnetic field generated in the interior. The cloud disappearance connects to photochemical aerosol production that depends on stratospheric dynamics influenced by interior heat. Even the ring arc confinement connects to the gravitational properties of the moons that orbit in the interior-generated gravitational field of the planet. Understanding Neptune as a system requires understanding its interior, and the magnetic field is the most direct observational window into that interior that is currently available. Neptune's magnetic field is fundamentally different in character from the magnetic fields of Earth, Jupiter, and Saturn, and this difference reflects a difference in the interior structure where the field is generated. Earth's magnetic field is produced by convective motion of liquid iron in the outer core, a process that generates a roughly dipolar field with the magnetic axis within about 11 degrees of the rotation axis and centered close to the planet's center. Jupiter and Saturn both have magnetic fields that fit a similar basic picture: large-scale, roughly symmetric convective flows in their layers of electrically conducting metallic hydrogen produce fields that are predominantly dipolar, with moderate tilts relative to the rotation axis. These fields are powerful, well-organized, and not surprising given the large volumes of conducting fluid that generate them. Neptune's field is tilted approximately 47 degrees from the rotation axis, more than 4 times the tilt of Earth's field. More unusually, the centre of the magnetic field is displaced from the centre of the planet by approximately 0.55 of Neptune's radius. This means the magnetic field is not only strongly tilted, but spatially asymmetric, with the field strength at the planet's surface varying dramatically from one location to another, depending on whether that location is close to or far from the offset magnetic centre. The result at the atmospheric level is an auroral pattern that appears at mid-latitudes rather than near the geographic poles, concentrated at the latitudes where the asymmetrically distributed magnetic field lines most efficiently channel charged particles into the atmosphere. This is what JWST detected in 2025. Aurora at the positions predicted by a magnetic field model that is tilted, offset, and fundamentally different in architecture from anything familiar in the inner solar system. The theoretical explanation for this unusual magnetic geometry involves the depth at which the dynamo operates and the physical state of the material generating it. In Jupiter and Saturn, the dynamo occupies a large fraction of the planetary volume in the deep layers of metallic hydrogen. Metallic hydrogen is ordinary hydrogen compressed to the point where electrons are no longer bound to individual protons, but instead form a sea of free electrons moving through the proton lattice, making the material electrically conductive in the same way that metals are. Large-scale, organized convective flows in this large conducting volume produce the roughly symmetric, predominantly dipolar magnetic fields that Jupiter and Saturn possess. In Neptune, there is no metallic hydrogen. The planet is an ice giant, and its interior is dominated by water, ammonia, and methane, under conditions that produce a fundamentally different kind of electrical conductivity. At the temperatures and pressures expected in Neptune's mantle, roughly 2,000 to 7,000 Kelvin and 1 to several million atmospheres, water, ammonia, and methane enter states that are quite different from their familiar surface forms. Water in this regime may reach what is called the superionic state, in which the oxygen atoms form a rigid crystalline lattice, while the hydrogen ions, effectively bare protons, are free to move through the lattice. The mobile protons make the material electrically conducting, but the conducting layer is thinner and more geometrically constrained than the metallic hydrogen regions in Jupiter and Saturn. A dynamo generated in this thin shell of superionic or ionic conducting material rather than in the large, deep volume of metallic hydrogen would naturally produce a more chaotic, less organized magnetic field, with larger tilts and offsets from the rotation axis. The 47-degree tilt and 0.55 radius offset of Neptune's observed field are consistent with this picture, though matching the specific geometry requires detailed modelling of the flow patterns within the conducting shell. The consequences of this unusual magnetic architecture extend throughout the Neptune system in ways that are directly relevant to JWST's observations. The auroral emissions that JWST detected in 2025 are not at fixed geographic locations as Earth's auroras are. Because the magnetic axis sweeps through a wide range of latitudes as Neptune rotates, the geographic positions where magnetic field lines most efficiently funnel charged particles into the atmosphere change continuously over Neptune's 16-hour rotation period. At any given moment, the aurora is concentrated at the latitudes and longitudes that happen to be aligned with the magnetic field's most active precipitation zones. Over a full rotation, the aurora traces out a complex pattern across the planet's atmosphere that reflects the three-dimensional structure of the magnetic field, rather than the planet's simple geographic coordinates. Mapping this pattern with JWST's NIR spec through multiple observation epochs, each capturing the aurora at different rotational phases, allows reconstruction of the magnetic field geometry from the auroral distribution in a way that is independent of the direct magnetometer measurements. Voyager 2 made in 1989. This independent constraint is scientifically valuable because it can reveal whether the magnetic field has changed in the 36 years since Voyager's single-point measurements, and it can detect time variability in the magnetic field on timescales of years that no single flyby could ever have captured. The magnetic field itself may not be static. If the convective flows in Neptune's superionic mantle layer that generate the dynamo are variable, the resulting magnetic field could show detectable changes on observable timescales. JWST's ongoing auroral monitoring is beginning to build the multi-epoch dataset needed to test this possibility, connecting the visible atmospheric glow of charged particle precipitation to the dynamics of the conducting interior layers several thousand kilometers below. The aurora that took 34 years to find. In March 2025, a team led by Henrik Melin at Northumbria University published a paper in Nature Astronomy that announced the first direct detection of auroras on Neptune. The finding made headlines in the planetary science community not merely because auroras on Neptune are scientifically interesting, but because finding them at all required a telescope that did not exist when the hunt for them began, and because the instrument that finally detected them was not primarily designed for this purpose. The molecule that betrayed Neptune's auroras was H3+, a triatomic hydrogen ion consisting of 3 protons sharing 2 electrons. H3+ forms when energetic charged particles, primarily electrons and protons guided along magnetic field lines, collide with molecular hydrogen in a planet's upper atmosphere. The collisions ionize and dissociate hydrogen molecules, producing atomic hydrogen and free electrons, and those products then recombine with remaining hydrogen molecules to produce H3+. Once formed, H3+ emits infrared light at specific, well-characterized wavelengths as it vibrates and rotates between quantum energy states. This infrared emission is the signature of auroral activity, and it is detectable only by an infrared spectrograph sensitive enough to pull the signal out against the thermal background of the planetary atmosphere. H3+ had been detected in the auroras of Jupiter, Saturn and Uranus for years before the Neptune detection. On Jupiter, H3+ emission is bright enough to be detected from ground-based telescopes with moderate aperture infrared instruments. On Saturn, the signal is weaker but still accessible from the ground under good conditions. Uranus presented more difficulty, requiring the best available ground-based infrared instruments, but the signal was eventually confirmed. Neptune, the farthest and coldest of the 4 giant planets, was the holdout. Its H3+ emission had been searched for and not found repeatedly. Every instrument pointed at Neptune in search of H3+ had come up empty. The reason Neptune's auroral H3+ emission had evaded detection was a combination of factors. Neptune is approximately 3 times farther from Earth than Uranus, making its H3+ emission roughly 9 times fainter at Earth's distance due to the inverse square law. Neptune's upper atmosphere is colder than those of Jupiter and Saturn, which means the H3+ in Neptune's ionosphere emits less efficiently because H3+ emission intensity depends on temperature. And Neptune's unusual magnetic field, tilted 47 degrees from the rotation axis and offset from the planet's center, produces an auroral morphology that spreads the emission across a wide range of latitudes rather than concentrating it at predictable polar locations, diluting any detectable signal further. JWST's NIR spec instrument changed the detection calculus decisively. NIR spec can collect the spectrum of a planetary target at multiple wavelengths simultaneously, with a sensitivity more than an order of magnitude greater than the most capable previous infrared spectrographs. When Melin's team pointed NIR spec at Neptune in June 2023 and examined the resulting spectrum, the H3+ emission lines were present. Not faintly present, not ambiguously present, but clearly detectable above the background, identifiable by their specific wavelengths at 3.5 and 4.0 micrometers, consistent with H3 plus emission at a temperature of approximately 358 Kelvin. The auroras appeared not at the geographic poles, where auroras would concentrate if Neptune's magnetic field were roughly aligned with its rotation axis, the way Earth's field is. They appeared at mid-latitudes, displaced from the poles by the same 47-degree tilt of the magnetic axis. The spatial distribution of the auroral emission, mapped from the spectral data, showed the mid-latitude concentration that magnetic field models had predicted, based on Voyager 2's magnetometer data. The detection was therefore not just a discovery of auroras, but a validation of Neptune's magnetic field geometry using an independent observational technique. Lead author Melin stated in the press release, "This is an incredible discovery from a scientific perspective. We have been waiting to observe auroras on Neptune for a very long time. We now have the tools to start to understand how Neptune's extraordinary magnetic field affects its upper atmosphere." The extraordinary magnetic field he referred to is the source of the second major finding in the same paper, the ionospheric temperature measurement that revealed the 400 Kelvin cooling since Voyager 2. The ionosphere that cooled by half. The same NIR spec observations that detected Neptune's auroras provided the temperature measurement that may ultimately prove more scientifically significant than the aurora detection itself. H3 plus emission intensity and the shape of its spectral features are sensitive functions of temperature. By measuring the relative intensity of different H3 plus emission lines in the NIR spec spectrum, Melin's team was able to calculate the temperature of the ionosphere where the H3 plus is located. The result was 358 Kelvin, approximately 85 degrees Celsius. Voyager 2's ultraviolet spectrometer measured Neptune's ionospheric temperature in 1989 at approximately 750 Kelvin, around 477 degrees Celsius. The two measurements, separated by 34 years, describe a dramatic change. The temperature of Neptune's ionosphere has fallen by approximately 392 Kelvin since Voyager flew through the system. That is a reduction to roughly 48% of the original value. The ionosphere has lost more than half of its thermal energy relative to what Voyager measured. Understanding why requires understanding what determines ionospheric temperature in the first place. The ionosphere is the uppermost layer of Neptune's atmosphere, where the gas density is so low that individual molecules can travel long distances without colliding with one another. At these altitudes, atoms and molecules are exposed directly to solar extreme ultraviolet radiation and to the particle flux from the solar wind and from Neptune's own magnetospheric environment. Solar EUV photons photoionize atoms and molecules, depositing energy that heats the gas. Charged particles guided along magnetic field lines into the atmosphere during auroral events deposit additional energy. The cooling side of the energy balance is dominated by infrared emission from the molecules and ions present in the ionosphere. H3+ is particularly important as a coolant because its infrared emission lines are efficient radiators. When H3+ forms in the upper atmosphere, it quickly reaches rotational and vibrational equilibrium with the surrounding gas and then radiates at its characteristic wavelengths, carrying energy away from the ionosphere into space. The efficiency of this cooling depends on the density of H3+, which depends on the balance between formation, driven by energetic particle precipitation, and destruction, driven by chemical reactions and the loss of ions to lower atmospheric layers. For the temperature to have halved in 34 years, either the heating has significantly decreased, the cooling has significantly increased, or both. A decrease in solar EUV heating is plausible if solar activity has changed, but the change required would need to be large and sustained in a way that is not consistent with observed solar cycle variations. An increase in H3+ cooling could occur if the abundance of H3+ in the ionosphere has increased due to enhanced auroral particle precipitation, but this would require a sustained increase in magnetospheric activity that has not been independently established. The paper's authors acknowledge that the factor of 2 cooling is not easily explained by any single mechanism within existing models, and called for continued JWST observations to track whether the temperature remains at its current value, continues to decline, or returns toward the 1989 Voyager value. The answer would help discriminate between different physical mechanisms. If the cooling is a transient feature related to a temporary decrease in auroral activity, the temperature might recover on observable timescales. If it is part of a long-term trend driven by some secular change in Neptune's magnetospheric or atmospheric properties, it might continue. Either outcome would constrain the physics of ice giant ionospheres in ways that go beyond Neptune to inform understanding of Uranus and of ice giant exoplanets throughout the galaxy. The co-discovery of auroras and the ionospheric cooling in the same paper is scientifically important because the two findings are physically connected. Auroral energy input is one of the primary heating mechanisms for ice giant ionospheres. If Neptune's ionosphere has cooled dramatically since 1989, and if JWST has simultaneously detected auroral activity that is presumably depositing energy into that ionosphere, then either the current auroral activity is weaker than the auroral activity Voyager 2 would have observed in 1989, or the cooling mechanism has become more efficient, or both. The two measurements together constrain the energy budget in a way that neither measurement alone could provide. The solar cycle at 30 astronomical units, a connection nobody expected. The proposal that Neptune's atmospheric properties, including its cloud coverage, its stratospheric temperature, and potentially its ionospheric temperature, are modulated by the 11-year solar cycle, is one of the most counterintuitive ideas to emerge from the accumulation of Neptune observations over the past 2 decades. Counterintuitive not because solar cycles are mysterious, they are well characterized from decades of solar monitoring, but because at Neptune's distance of 30 astronomical units, the Sun is a very faint star. The idea that its 11-year activity cycle would leave a detectable imprint on a planet receiving barely 1/1000th of Earth's solar flux requires a mechanism precise enough to matter at this extreme distance. The Roman et al. 2022 study was the first to identify a possible solar cycle correlation in Neptune's stratospheric temperature record. The correlation was not tight or unambiguous. The 17-year dataset they assembled covered only about 1.5 solar cycles, which is insufficient to establish a periodicity with confidence. The authors were careful to present it as a tentative suggestion rather than a firm result. But the timing of the stratospheric cooling, coinciding with the declining phase of solar cycle 24, and the timing of the subsequent cloud disappearance documented by Chavez et al. In 2023, coinciding with the solar minimum between cycles 24 and 25, gave the solar cycle hypothesis enough circumstantial support that it demanded further investigation. The physical mechanism proposed connects solar ultraviolet flux to Neptune's atmospheric chemistry. UV radiation from the Sun drives photochemical reactions in planetary atmospheres even at great distances, because UV photons are energetically capable of breaking molecular bonds and initiating reaction chains regardless of how faint the UV flux is, as long as the reactions they initiate are sensitive to the specific photons available. On Neptune, the UV flux drives the production of complex hydrocarbon molecules and aerosol particles in the stratosphere. These aerosols, as discussed in the context of the cloud disappearance, can serve as condensation nuclei for methane ice clouds. They also contribute to stratospheric thermal balance by absorbing and scattering light in ways that affect how the stratosphere heats and cools. if solar UV flux variations over the 11-year cycle are large enough relative to the background UV level to significantly alter the photochemical production rate of stratospheric aerosols, and if those aerosols play an important enough role in the stratospheric energy balance to produce detectable temperature changes, then the solar cycle connection is physically plausible. The magnitude of solar UV variation over a cycle is roughly 10 to 20%, and whether this is sufficient to drive the observed 8 degrees Celsius stratospheric temperature change on Neptune is a quantitative question that requires detailed photochemical modelling. The lag time between solar UV changes and observable atmospheric responses on Neptune introduces an additional complication. Photochemical reactions take time to process solar UV changes into changes in aerosol abundance and radiative properties. The transport of those changes through the stratosphere takes additional time. The total lag between a change in solar UV flux and the resulting change in observable cloud coverage or stratospheric temperature could be months to years. Estimating this lag from the available data is difficult with only 1 or 2 solar cycles of observations, but the data suggest a lag of approximately 2 years between UV changes and cloud response. Testing this lag timescale with longer datasets as solar cycle 25 progresses is one of the primary motivations for continued JWST monitoring of Neptune through the next decade. If the solar cycle connection is confirmed through additional cycles of monitoring, it would have significant implications for understanding ice giant atmospheres more broadly. It would mean that even at 30 astronomical units, a planetary atmosphere is not decoupled from its host star's activity cycle. It would imply that the photochemical response of ice giant atmospheres to stellar UV is sensitive enough to matter even at very low absolute flux levels. And it would provide a template for understanding how the atmospheres of ice giant exoplanets in distant orbits around other stars might respond to their host stars' activity cycles, which is relevant to assessing the long-term habitability of any moons or smaller bodies in those systems. What JWST's Neptune program looks like over the next decade. The observations discussed in this script represent the opening phases of what is planned as a multi-year JWST observational campaign of the Neptune system. The scientific team responsible for these observations, led by Hamill as principal scientist, with a constellation of collaborating researchers at universities and institutes across the United States, Europe, and beyond, has submitted and received approval for observation programs that extend JWST's Neptune coverage across multiple years and multiple instruments. The overarching scientific goal of this extended program is to characterize how Neptune's atmosphere, ionosphere, ring system, and moon system change over time. Single observations are scientifically valuable, as the first NIR-CAM image and the NIR-SPEC aurora detection demonstrated, but time series observations, in which the same target is observed repeatedly with the same instruments under comparable conditions, are what allow scientists to identify trends, seasonal variations, responses to solar activity, and other temporal changes that cannot be detected from a snapshot. For the stratospheric temperature question, the program aims to continue the observational record established by the ground-based studies, now with JWST's superior sensitivity and from above Earth's atmosphere, which eliminates the contamination that ground-based infrared observation must deal with from water vapor and other gases in Earth's own atmosphere. If stratospheric temperatures have been cooling during southern summer, as the Roman et al. Data showed, JWST observations over the next several years will either confirm the cooling continues, show that it has leveled off, or reveal that temperatures are beginning to recover as Neptune progresses towards southern autumnal equinox. All three outcomes would constrain the seasonal and solar cycle models differently. For the ionospheric temperature and the aurora, Continued NIR spec observations will track whether the 358 Kelvin temperature measured in 2023 is stable, continuing to decline, or beginning to recover. The shape of the temperature evolution over time, whether it follows a solar cycle pattern, a seasonal pattern, or some other periodicity, will guide interpretation of the cooling mechanism. These observations will also continue to map the spatial distribution of auroral activity across Neptune's disk, tracking how the auroral morphology evolves as Neptune rotates and as the viewing geometry from Earth changes over the years. For Triton specifically, the program includes dedicated NIR spectroscopic observations of the Moon's surface in multiple wavelength ranges. The goal is to map the distribution of nitrogen, methane, carbon dioxide, carbon monoxide, and complex organic compounds across Triton's visible surface with a spatial resolution and spectral detail not previously achievable. Particular attention is being paid to spectral features that would be consistent with material transported from a subsurface liquid reservoir to the surface through volcanic or cryovolcanic processes. Confirming or ruling out such activity would significantly advance the question of Triton's potential for hosting liquid water environments. The ring system observations are designed to extend the temporal baseline for ring monitoring with infrared sensitivity. The ring particle properties measured in the 2022 NIR CAM image represent a single snapshot at a single wavelength combination. Repeated observations at different infrared wavelengths and eventually at multiple epochs, allowing direct comparison, will constrain how ring particle sizes and compositions are distributed and whether they change over time. The Adams ring arcs, whose stability has been a puzzle since Voyager, will be monitored to determine whether their positions and relative brightnesses are changing in ways that test the resonance confinement models. The cloud monitoring program that began with the discovery of the cloud disappearance will continue through at least a full solar cycle of observations. If the solar UV hypothesis is correct, clouds should begin to recover as solar cycle 25 progresses toward its maximum and then potentially decline again as the cycle moves toward its next minimum. Tracking this behavior with JWST's infrared sensitivity combined with continued Keck observatory monitoring in visible wavelengths will provide a two-wavelength view of the cloud evolution that probes different altitude ranges simultaneously. A particularly important aspect of this long-term campaign is that it arrives at a unique moment in Neptune's seasonal cycle. Neptune requires 164.8 Earth years to complete one orbit around the Sun, meaning each season lasts more than 4 decades. Humanity has only been observing Neptune with modern instruments for a tiny fraction of a single Neptunian year. Voyager 2's flyby in 1989 occurred during southern summer. The ground-based observations analysed by Roman and colleagues track part of that same season. JWST is now observing the planet as it slowly transitions away from southern summer toward autumn. In practical terms, scientists are witnessing a seasonal evolution that no previous generation of astronomers has ever had the opportunity to study. This creates a rare scientific situation in which observations separated by decades are not simply historical records, but essential pieces of a single atmospheric experiment being conducted by nature itself. Every new observation can be compared against Voyager measurements, against ground-based observations from the early 2000s, and against JWST's own growing archive. The resulting timeline allows researchers to separate temporary fluctuations from genuine long-term trends, and to identify which atmospheric processes are driven by seasonal forcing and which arise from internal dynamics. The value of these observations extends beyond Neptune alone. Ice giants occupy a major category of planets throughout the galaxy. Surveys from Kepler and TS have shown that planets between the sizes of Earth and Neptune are among the most common planetary types discovered around other stars. Yet within our own solar system, Uranus and Neptune remain the only examples available for detailed study. Every improvement in understanding Neptune's atmosphere, chemistry, magnetic environment, and internal energy transport contributes directly to the interpretation of thousands of distant exoplanets that can never be studied at comparable resolution. There is also the possibility that some of Neptune's current mysteries will reveal entirely new atmospheric physics. The unexplained stratospheric cooling, the dramatic cloud variability, the unexpectedly cold ionosphere, and the unusual auroral behavior may ultimately prove to be connected manifestations of processes that existing models do not adequately capture. Scientific history repeatedly shows that the most important discoveries often emerge not from confirming predictions, but from investigating observations that refuse to fit them. For that reason, the Neptune program is not simply a campaign to gather better images of a distant planet. It is an effort to understand a world that has repeatedly demonstrated its ability to surprise astronomers. Every new dataset adds another piece to a puzzle that began with Voyager more than 3 decades ago, and that JWST has now transformed into one of the most intriguing ongoing investigations in planetary science. The answers may take years to emerge, but for the first time since Neptune was discovered through mathematics in 1846, astronomers possess an instrument capable of following the planet's changes in sufficient detail to uncover why this distant ice giant behaves so differently from expectations. Neptune's interior through an infrared window. One of the less discussed but scientifically significant aspects of JWST's Neptune program is what infrared measurements reveal about the planet's deep interior, a region that no spacecraft has ever directly probed and that is unlikely to be directly sampled within any near-future mission timeline. The connection between the observable atmosphere and the deep interior runs through the mechanisms of convection and heat transport, and JWST's thermal measurements are providing new constraints on how this connection works. Neptune's interior is understood from theoretical modelling informed by the planet's total mass, mean radius, and gravitational field harmonics measured from the orbital perturbations the planet induces on its moons. These constraints support a 3-layer structure, an outer atmosphere of hydrogen, helium, and methane ices, an intermediate mantle of water, ammonia, and methane in a high-pressure ionic or superionic state, and an inner core of silicate and iron-rich material similar in composition to a rocky planet. The boundary between the atmosphere and the mantle is not a sharp phase transition, but a gradual increase in density with depth, and the exact depths and compositions of these layers are uncertain within ranges that affect the predictions for how heat flows from the interior to the surface. The superionic mantle is the most exotic of these layers. Under conditions of temperature and pressure expected at Neptune mantle depths, water, ammonia, and methane undergo transformations that have only recently been studied in laboratory shock compression experiments. In the superionic state, the oxygen atoms of water molecules form a fixed lattice structure, while the hydrogen ions, essentially bare protons, flow freely through that lattice, conducting electricity like a metal, while the oxygen lattice remains solid. This state simultaneously exhibits properties of a solid and a liquid, a phase of matter with no everyday analogue. The electrical conductivity of the superionic mantle is thought to be what generates Neptune's magnetic field. The convective flow of this conducting material, driven by the internal heat escaping upward, acts as a dynamo. But because the superionic mantle is relatively thin compared to the metallic hydrogen dynamo regions in Jupiter and Saturn, and because convective flows in a thin conducting shell tend to be more chaotic and less organized than flows in a deep spherical region, the resulting magnetic field is irregular and non-dipolar in the way described earlier. JWST's thermal measurements constrain this interior model in a specific way. The total thermal emission from Neptune measured at mid-infrared wavelengths by MIRI, determines the total power the planet is radiating to space. Subtracting the solar energy absorbed by the planet gives the internal heat flux, the power flowing outward from the interior through the atmospheric layers to space. This internal heat flux sets the boundary condition at the top of the atmospheric column that convective models must satisfy. If the atmosphere is transporting a certain amount of internal heat upward by convection, the atmospheric temperature profile must follow a specific pattern determined by the convective energy transport. Measuring that temperature profile with NIR spec constrains how efficiently the atmosphere is transporting internal heat, and therefore provides information about the convective properties of the atmospheric layers, which in turn reflect the rate at which heat is being delivered from the deep interior. Current models of Neptune's cooling history predict a specific internal heat flux that depends on the initial temperature of the planet after formation and the thermal conductivity of its mantle. If the internal heat flux measured by JWST is significantly different from what those models predict, it would require revision of the initial conditions assumed for Neptune's formation or the thermal properties assumed for its mantle. Either revision would propagate into models of ice giant formation more generally, with implications for understanding the planetary system being characterized by JWST around other stars. What makes this especially important is that Neptune may be one of the best natural laboratories available for studying a class of planets that appears to be extraordinarily common throughout the galaxy. Many of the exoplanets discovered by the Kepler and TESS missions fall into the size range between Earth and Neptune, yet astronomers possess only limited observational constraints on how such worlds evolve internally over billions of years. Neptune therefore functions as a nearby benchmark against which distant exoplanet observations can be tested. If JWST observations reveal that Neptune's interior transports heat differently than current models predict, then assumptions being applied to thousands of exoplanets may also require revision. In this sense, every thermal measurement of Neptune extends beyond the planet itself. It becomes a test of planetary physics under conditions that cannot be reproduced in any laboratory on Earth, and a guide for interpreting entire populations of ice giants scattered throughout the Milky Way. Triton's surface chemistry and the subsurface ocean question. Triton's potential for hosting a subsurface liquid water ocean is one of the most compelling astrobiological questions in the outer solar system, and it is one that JWST is uniquely positioned to advance. The chain of reasoning that leads from a retrograde orbiting captured Kuiper Belt object to a potentially habitable subsurface environment involves several physical processes, each of which carries its own uncertainty. But the cumulative case is stronger than it is sometimes presented. Triton's rocky interior contains radioactive elements, uranium, thorium, and potassium-40, whose decay produces heat continuously. The rate of radiogenic heat production depends on the abundance of these elements in Triton's rock, which can be estimated from Triton's bulk density and from the compositional models of Kuiper Belt objects. Estimates of Triton's radiogenic heat flux suggest that it could be sufficient to maintain a thin liquid layer at the boundary between the rocky core and the overlying ice shell, provided that the ice shell is thick enough to insulate the interior against the extreme cold of the surface, which is at approximately -235 degrees Celsius. Tidal heating provides an additional heat source that is less certain but potentially important. Triton's retrograde orbit around Neptune is slowly decaying due to tidal interactions between the Moon and the planet. As the orbit shrinks, the tidal forces that Neptune exerts on Triton change, and the frictional heating of Triton's interior from these changing tidal forces may contribute to the total heat budget. The magnitude of tidal heating depends on the orbital eccentricity and on the internal structure of Triton, parameters that are not well constrained, but upper bounds on the tidal heating rate suggest it could be non-negligible relative to the radiogenic heat flux. If a liquid water ocean exists at Triton's interior, the question of whether JWST can detect evidence for it comes down to whether material from that ocean reaches the surface in a way that leaves a chemical or mineralogical signature detectable in infrared spectroscopy. The most promising pathway would be cryovolcanic activity, geological processes analogous to volcanism but involving liquid water or briny water-ammonia mixtures rather than silicate magma. If liquid material from the subsurface ocean erupts through the ice shell, it would deposit material on the surface whose composition reflects the ocean chemistry, potentially including salts, ammonia compounds, organic molecules, or other species that would not be present if Triton's surface chemistry were determined solely by the deposition of external material and surface photochemistry. Voyager 2's detection of active geysers on Triton already established that Triton is geologically active in the solar greenhouse sense. But whether the geyser activity involves material transported from depth or is driven entirely by near-surface solar heating of the frost layer is uncertain. The geyser plumes observed by Voyager appeared to originate from within the south polar frost cap and to consist primarily of dark material carried upward by sublimating nitrogen gas. This is consistent with the solar greenhouse mechanism and does not require any connection to a deep subsurface reservoir. But JWST's spectroscopic capability can look for compositional inhomogeneities on Triton's surface that would be inconsistent with pure solar greenhouse activity, specifically the presence of non-volatile salts or organic molecules at specific locations that would be expected if cryovolcanic material from a saline subsurface ocean had been deposited there. Early results from JWST's Triton spectroscopy have not yet been published as of early 2026, but the data obtained during the June 2023 observations that also detected the aurora are understood to be in the analysis pipeline. The scientific community is watching for these results carefully because a positive detection of cryovolcanic surface deposits on Triton would be one of the most significant astrobiology findings from JWST's solar system program, extending the list of potentially habitable ocean worlds in the outer solar system and providing the first remote spectroscopic evidence for a Kuiper Belt-derived ocean world. The diamond rain hypothesis and what we actually know. Among the most visually evocative ideas in Neptune science is the hypothesis that diamonds rain through Neptune's interior, crystallizing from the carbon in compressed methane molecules under the planet's extreme pressure and temperature conditions and falling through the mantle toward the core. This idea has appeared in countless popular science articles and documentary programs, and it deserves careful examination both for what it actually proposes and for what the evidence actually supports. The core of the idea is chemically and physically sound. At the pressures and temperatures expected in Neptune's mantle, approximately 1 to several million times atmospheric pressure and temperatures of several thousand Kelvin, theoretical calculations and laboratory experiments both indicate that methane molecules, which consist of one carbon atom bonded to 4 hydrogen atoms, decompose. The carbon atoms released by this decomposition are subjected to pressures sufficient to stabilize the diamond form of carbon, the densest stable allotrope under these conditions. The hydrogen released simultaneously becomes part of the high-pressure fluid environment. Laboratory experiments at the SLAC National Accelerator Laboratory, published in 2022, used a laser-driven compression technique to create the pressure and temperature conditions expected in ice giant mantles and directly observed diamond formation from hydrocarbon starting materials. The experiment found that diamond nanocrystals formed rapidly under these conditions, providing direct experimental confirmation that the chemistry is physically possible at the relevant conditions. The experiment was conducted on polystyrene, a hydrocarbon plastic, rather than on methane directly. but the underlying chemistry involves the same carbon-hydrogen bonds and the same pressure-temperature regime. What the laboratory experiments do not directly confirm is the macroscopic behavior of these diamond crystals inside a real planetary interior. In the planet, the newly formed diamond crystals would be denser than the surrounding fluid and would therefore sink. As they sink into deeper and hotter layers, they would eventually reach conditions where diamond is no longer thermodynamically stable relative to a liquid carbon phase, at which point the solid diamonds would melt into liquid carbon. This liquid carbon would then pool at the boundary with the planet's rocky core, forming a layer of liquid carbon around the core. The overall picture is of diamond crystals forming in the mid-mantle, sinking, melting into liquid carbon at greater depth, and gradually accumulating at the core boundary over billions of years. The connection to JWST's observations is indirect but real. The total heat that Neptune radiates, measured by MIRI, must be accounted for by the combination of primordial heat retained from formation and heat generated by ongoing processes in the interior. The conversion of gravitational potential energy to heat as diamond crystals sink through the mantle is one such ongoing process, sometimes called gravitational differentiation, and it could contribute a non-negligible fraction of the observed excess thermal emission. If JWST's precise measurement of Neptune's total thermal output, combined with improved models of the opacity and thermal structure of the atmosphere, narrows the uncertainty in the internal heat flux, it becomes possible to constrain more tightly whether differentiation processes like diamond sinking are contributing significantly to the heat budget. The diamond rain hypothesis also has implications for Neptune's magnetic field. If a layer of liquid carbon is accumulating at the core boundary, this layer is electrically conductive and participates in the planetary dynamo that generates Neptune's magnetic field. The specific properties of the liquid carbon layer, its electrical conductivity, its thickness, and its interaction with the superionic mantle above and the silicate core below would affect the magnetic field geometry in ways that could in principle be detected through precise measurements of the field structure. The connection between the atmospheric aurora that JWST detected and the deep interior processes that generate the magnetic field driving that aurora is therefore a chain that runs from the observable ionosphere all the way to the diamond-producing chemistry of the deep mantle. Diamond formation is also important because it represents a mechanism for chemically separating Neptune's interior over time. When carbon is locked into dense diamond crystals and transported downward, the composition of the surrounding mantle gradually changes. Regions that have lost carbon become relatively enriched in hydrogen and other volatile compounds, while deeper layers accumulate increasing amounts of carbon-rich material. Over billions of years, this process can produce a stratified interior in which different chemical species occupy different depths according to their density and thermodynamic stability. Such stratification affects how efficiently heat is transported outward, because composition gradients can suppress large-scale convection and create layers that act as barriers to mixing. This possibility has become increasingly relevant in recent theoretical studies of ice giant evolution. Models attempting to explain Uranus and Neptune's very different thermal behaviors, despite their similar masses and compositions, often invoke internal layering as a key factor. Uranus radiates surprisingly little excess heat, while Neptune emits more than twice the energy it receives from the Sun. One proposed explanation is that Uranus possesses stronger compositional stratification that traps heat in its deep interior, whereas Neptune's interior remains more effectively mixed, allowing heat to escape. If diamond formation and carbon transport contribute to these composition gradients, they may play a role in determining why the two planets evolved so differently despite their apparent similarities. The implications extend beyond Neptune itself. Ice giants appear to be among the most common classes of planets discovered around other stars. Many exoplanets identified by missions such as Kepler and TESS fall into the size range between Earth and Neptune, suggesting that interiors dominated by high-pressure water, methane, and ammonia may be common throughout the galaxy. Understanding whether diamond formation is a routine consequence of ice giant chemistry therefore influences not only our picture of Neptune, but also our interpretation of thousands of distant worlds. Every improvement JWST provides in constraining Neptune's internal heat flow, atmospheric structure, and energy budget helps refine the models used to describe an entire population of planets beyond the solar system. In that sense, the idea of diamond rain is not merely a scientific curiosity. It represents a tangible example of how extreme planetary environments can produce forms of matter and geological processes that have no equivalent on Earth. Deep beneath Neptune's cloud tops, under pressures and temperatures far beyond anything encountered in the terrestrial environment, carbon may be cycling through solid, liquid, and perhaps even supercritical phases, releasing energy and reshaping the planet's interior. JWST cannot observe these diamonds directly, but by measuring the heat escaping from the planet and the atmospheric conditions through which that heat travels, it is providing some of the strongest observational constraints yet on whether this remarkable process is occurring. What a Neptune mission would look like and why it has not happened. The scientific richness revealed by JWST's Neptune observations stands in sharp contrast to the fact that only one spacecraft has ever visited Neptune, and that spacecraft flew past it in 1989 on a trajectory that did not allow it to enter orbit or conduct sustained observation of any part of the system. Every discovery described in this script, the stratospheric cooling, the cloud disappearance, the aurora, the ionospheric temperature halving, the ring detail, the polar brightness, has been made with instruments operating at distances of billions of kilometres, not from a spacecraft in the Neptune system. The case for a dedicated Neptune orbiter mission has been made by planetary scientists repeatedly over the past 2 decades. The 2023 to 2032 Planetary Science and Astrobiology Decadal Survey, the strategic planning document that guides NASA's planetary science investment priorities, ranked a Uranus orbiter and probe as the highest priority large flagship mission for the decade. Neptune was not ranked as highly, but the report acknowledged the scientific value of a Neptune system mission and noted that a Uranus mission would inform the design of future Neptune missions by developing the technologies and expertise needed for ice giant exploration. The challenges facing a Neptune mission are substantial and primarily logistical rather than scientific. Neptune's distance makes travel time long under any realistic propulsion scenario. A chemical propulsion mission to Neptune using a Jupiter gravity assist requires approximately 12 to 13 years of cruise time after launch. During that time, the spacecraft and its instruments must survive the space environment, and the mission team must maintain operations and expertise for more than a decade before any science data is collected at the target. The planetary alignment required for a fuel-efficient Jupiter gravity assist to Neptune is not continuously available. Specific launch windows occur at intervals of years, and missing a window means waiting for the next one and potentially accepting a longer or less efficient trajectory. The spacecraft itself must carry sufficient propellant to enter Neptune orbit rather than simply flying past. Orbital insertion at Neptune requires slowing the spacecraft by several kilometers per second to be captured by Neptune's gravity, which demands a large propellant load that adds mass and cost to the mission. A nuclear power source is essentially mandatory, since Neptune's distance makes solar power impractical for anything beyond basic housekeeping functions. And radioisotope power systems require specialized manufacturing and testing infrastructure that exists at a limited scale. China's proposed Neptune mission with a launch window around 2033, represents the most concrete near-term possibility for a new spacecraft at Neptune. If launched on schedule, this mission would arrive at Neptune in the mid-2040s, adding a roughly half-century gap between the Voyager 2 flyby and the next close-up observation of the Neptune system. Details of the scientific payload and mission profile have not been fully published as of early 2026, but the proposed mission has been presented at international planetary science conferences as including an orbiter and potentially an atmospheric probe. An atmospheric probe at Neptune would be particularly scientifically valuable. Dropping a probe into Neptune's atmosphere would allow direct measurement of the abundances of helium, neon, argon, krypton, xenon, hydrogen, methane, and other species as a function of depth, characterizing the atmospheric composition with a precision that remote spectroscopy from JWST can approach, but not fully match. These measurements would constrain models of Neptune's formation and the specific region of the protoplanetary disk where it accreted, because the noble gas abundances and the deuterium to hydrogen ratio in the atmosphere carry signatures of the temperature and pressure conditions under which the planet's volatile envelope was captured. Until such a mission is funded, designed, launched, and eventually reaches Neptune, JWST remains the primary scientific instrument providing new data about the planet and its system. The discoveries described throughout this script represent what can be achieved with an infrared space telescope designed for cosmology and galaxy formation science, adapted for solar system observation with remarkable effectiveness. What a purpose-built Neptune mission would achieve is in some respects beyond what any current analysis can fully anticipate, because Neptune has a pattern of confounding expectations. The planet that keeps surprising every instrument pointed at it. The history of Neptune observation is a history of instruments discovering something unexpected. Voyager 2 found a system of moons whose diversity, from the retrograde Triton to the tiny shepherd moons near the rings, was not anticipated. It found winds faster than any other planet in the solar system on a world receiving almost no solar energy to drive them. It found active geological processes on Triton despite surface temperatures barely above absolute zero. It found ring arcs rather than complete rings. Ground-based observations with Hubble and the Keck Observatory found storms that appeared and dissolved on timescales of years, while Jupiter's storms persisted for centuries. They found an atmospheric temperature that cooled instead of warming as southern summer arrived. They found clouds that vanished. JWST found auroras that 34 years of searching had missed. It found an ionosphere that had cooled to half its previous temperature. It found rings with detailed structure in infrared that had been invisible for 3 decades. It found a polar brightness whose origin remains under investigation. The pattern is consistent. Every time a new instrument looks at Neptune with sufficient sensitivity, it finds something not in the prior model. This is not because Neptune is an unusual planet in the sense of being a rare type of object. Ice giants are, as noted, among the most common types of planets detected in exoplanet surveys. It is because Neptune's physics is genuinely complex, involving the interplay of internal heat, a strongly tilted and offset magnetic field, photochemistry driven by faint but consequential solar UV, captured moon dynamics, and a ring system with features that existing theory explains only partially. The complexity is real, and the instruments capable of probing it have only recently become available. What JWST is doing for Neptune is not simply providing better images of a known planet. It is providing the first systematic, multi-instrument, multi-year infrared observational campaign of an ice giant in the era of modern astrophysical instrumentation. The results so far, over the first 3 years of the observational program, have each been individually surprising and collectively suggest that the basic framework for understanding ice giant atmospheric physics needs substantial development. The scientists working on these results approach the surprises with a mixture of professional excitement and honest puzzlement. They have models that were developed from Voyager 2 data and refined over 3 decades of ground-based monitoring, and those models make specific predictions. JWST's observations are not confirming those predictions. The stratosphere is doing something the seasonal models did not predict. The ionosphere has cooled in a way that the energy balance models do not explain. The clouds responded to the solar cycle in a way that the photochemical models quantitatively reproduce only approximately. These are not failures of science, they are science. The models that fail against new data are the models that get revised, and the revised models are more accurate descriptions of Neptune than what came before. What the spectral lines know that we don't. Among the technical achievements underlying the Neptune aurora discovery, the one that receives the least popular attention is the role of spectral line analysis in extracting the temperature measurement from the NIR spec data. The technique involved is one of the most powerful in observational astrophysics, and understanding how it works illuminates why JWST could achieve what no previous instrument could for Neptune's ionosphere. Every atom and molecule, when in an excited state, can emit electromagnetic radiation at specific, precisely defined wavelengths as it transitions from a higher energy state to a lower one. These emission wavelengths are determined by the quantum mechanical structure of the atom or molecule and are the same everywhere in the universe. The 3.5 micrometer emission line of H3+ in Neptune's ionosphere is at exactly the same wavelength as the 3.5 micrometer emission line of H3+ in a laboratory on Earth, in a hydrogen cloud in the Milky Way, or in an exoplanet atmosphere 100 light-years away. This universality is what makes spectroscopy the most powerful tool in astrophysics. For H3+, the relevant emission lanes in the wavelength range JWST's NIR spec covers are transitioned between vibrational and rotational energy levels. H3+, being an asymmetric molecule with 3 protons and 2 electrons, has a rich spectrum with many lines at infrared wavelengths. The relative intensities of these lines depend on the temperature of the gas. At higher temperatures, the molecule has more energy distributed among higher vibrational and rotational states, so the transitions from those higher states are more probable, and the corresponding lines are brighter relative to the lines from lower states. At lower temperatures, the opposite is true, and the lower energy transitions dominate. By measuring the intensities of multiple H3+ emission lines simultaneously, which NIR spec can do, because it disperses the light from Neptune into a detailed spectrum covering many wavelengths at once, the team was able to determine the temperature of the gas producing those lines from the pattern of relative intensities. This is the Boltzmann excitation temperature, the temperature at which the observed distribution of excited states is consistent with thermal equilibrium. It is a remarkably direct thermometric technique that requires no assumptions about the mass, distance, or elemental composition of the source, only knowledge of the quantum mechanical properties of H3+, which are well established from laboratory spectroscopy. The precision of this temperature measurement depends on the signal-to-noise ratio of the spectrum. The more photons collected, and the better the spectral resolution, the more precisely the relative line intensities can be measured, and the more precisely the temperature can be determined. JWST's large mirror area, 6.5 meters in diameter compared to 2.4 meters for Hubble, and its cold, space-based environment free from Earth's atmospheric interference are what allowed the H3+ emission to be detected with sufficient signal to noise for a temperature determination. Previous instruments pointed at Neptune had seen hints of H3+ emission or set upper limits on its brightness, but none had achieved the detection significance and spectral quality needed for a reliable temperature measurement. The H3 plus temperature of 358 Kelvin measured from JWST data is therefore not a rough estimate or a model-dependent inference. It is a direct, model-independent measurement of the thermal state of the gas in Neptune's ionosphere, derived from fundamental quantum mechanics and independent of any assumptions about Neptune's interior or atmospheric structure. This directness is what makes its disagreement with Voyager's 750 Kelvin value so scientifically significant. There is no interpretive wiggle room to blame the discrepancy on different modelling assumptions or different spatial averaging. The gas was hotter in 1989 than it is now, and the spectral lines are the evidence. The robustness of the spectroscopic method also allows scientists to extract information beyond temperature alone. The exact shape, width, and position of emission lines contain additional physical information about the environment in which the light was produced. Thermal motion broadens spectral lines through the Doppler effect, as molecules moving toward or away from the observer slightly shift the wavelength of the photons they emit. Bulk atmospheric motions, including winds and circulation patterns, can introduce further Doppler shifts. In sufficiently high-quality spectra, these effects can be separated and analysed, transforming a simple detection of light into a diagnostic tool capable of probing the dynamics of an atmosphere thousands of millions of kilometres away. For Neptune, these possibilities are especially important because the ionosphere occupies a transitional region between the lower atmosphere and the surrounding space environment. Energy enters this region from multiple directions simultaneously. Solar ultraviolet radiation ionizes atmospheric gases from above. Charged particles guided by the planet's magnetic field deposit energy through auroral processes. Internal atmospheric waves generated deeper in the atmosphere can propagate upward and dissipate their energy at ionospheric altitudes. Distinguishing between these different energy sources requires measurements that are sensitive not only to temperature, but also to spatial structure and temporal variability. The H3 plus ion itself is particularly valuable because it acts as both a thermometer and a coolant. Once formed, it radiates efficiently in infrared wavelengths, carrying energy away from the ionosphere and helping regulate its temperature. In giant planet atmospheres, H3+ is often referred to as a thermostat because changes in temperature influence how efficiently the molecule emits radiation. A warmer ionosphere generally produces stronger infrared emissions, increasing radiative cooling and tending to counteract further temperature increases. Understanding the abundance and behaviour of H3+ is therefore central to understanding the overall energy balance of the upper atmosphere. This is one reason the unexpectedly low temperature measured by JWST has generated such interest. If Neptune's ionosphere has indeed cooled dramatically since the Voyager era, then something fundamental about its energy budget has changed. Either less energy is entering the ionosphere than before, more energy is escaping it, or both processes are occurring simultaneously. Each possibility points toward different physical mechanisms. Changes in solar ultraviolet output, variations in magnetospheric activity, shifts in atmospheric circulation, or long-term seasonal effects could all potentially contribute, but none currently explains the full magnitude of the observed cooling. The measurement also highlights the extraordinary continuity of planetary science across generations. The comparison being made today depends on data collected by Voyager 2 during a brief flyby in 1989 and data collected by JWST more than 3 decades later. The scientists analysing the recent observations are, in many cases, members of a generation that was not yet active in research when Voyager conducted its encounter. Yet because spectroscopy is grounded in immutable physical laws, the observations remain directly comparable across decades. The same quantum transitions observed in 1989 are observed today. The same molecular physics applies. the same spectral fingerprints can be measured and interpreted using increasingly powerful instruments. In that sense, the Neptune ionosphere temperature result is more than a measurement of a distant atmosphere. It is an example of one of astronomy's greatest strengths, the ability to connect observations separated by decades, spacecraft generations, and technological revolutions into a single, continuous scientific record. The spectral lines recorded by JWST are not merely signals from a remote planet. They are data points in an experiment that nature has been conducting for billions of years, and that humanity is only now beginning to observe with sufficient precision to understand. The planet at the edge, revisited. Neptune sits at the boundary between the planetary solar system and the Kuiper Belt, the vast reservoir of icy bodies that extends beyond Neptune's orbit and from which Triton was almost certainly captured. This position at the edge of the organized planetary system makes Neptune not just the last planet, but the gatekeeper of the outer solar system, the largest gravitational influence shaping the dynamics of the Kuiper Belt and determining which objects from that reservoir occasionally get flung inward as long-period comets. Understanding Neptune's mass distribution, its internal heat emission, and its magnetic field is relevant to understanding how the planet has shaped the outer solar system over its 4 billion-year history. The gravitational resonances that Neptune maintains with populations of Kuiper Belt objects, including the Plutinos that orbit in a 2 to 3 resonance with Neptune, are sensitive to the planet's mass and to its orbital history. Models of solar system formation that trace how Neptune migrated outward from its formation location through the outer solar system, scattering Kuiper Belt objects as it went, depend on the physical properties of the planet that JWST is now measuring with new precision. The same migration that scattered Kuiper Belt objects also delivered some of them into unstable orbits that eventually decayed into Neptune captures, of which Triton is the most prominent example. The rate of such captures and the properties of the objects captured depend on the details of Neptune's migration history. Characterizing Triton's composition with JWST spectroscopy therefore contributes to understanding not just Triton as an individual object, but the broader class of Kuiper Belt objects whose properties were set by the same processes that formed the outer solar system. This connection between Neptune's observable present and the solar system's historical past is one of the reasons planetary scientists argue for the scientific priority of Neptune missions and observations. The planet is not simply a point on a list of planets to be visited and checked off. It is a physical record of outer solar system formation and evolution, encoded in its rings, its captured moon, its internal heat, and its unusual magnetic field. JWST is reading parts of that record for the first time with instruments capable of the task. The significance of this record extends beyond the history of our own solar system. Over the past 2 decades, exoplanet surveys have revealed that planets comparable in size to Neptune are among the most common planetary types in the galaxy. In many planetary systems, worlds occupying the mass range between Earth and Neptune appear to outnumber both terrestrial planets and Jupiter-sized gas giants. Yet despite their apparent abundance elsewhere, humanity has studied only 2 ice giants up close, Uranus and Neptune, each visited only once by Voyager 2 in the 1980s. This creates an unusual situation in planetary science. Some of the most common planets in the galaxy remain among the least understood in our own solar system. The physical processes occurring inside Neptune, the transport of heat from its deep interior, the chemistry of its atmosphere, the operation of its magnetic dynamo, and the evolution of its moon system all serve as natural laboratories for understanding an entire class of planets that telescopes are now discovering around other stars by the thousands. The connection is especially important because direct observations of exoplanets remain limited. Even with JWST's extraordinary capabilities, most exoplanets appear as unresolved points of light. Scientists can infer atmospheric composition, estimate temperature, and sometimes constrain cloud properties, but the interpretation of those observations depends heavily on theoretical models. Those models must be tested against planets whose properties can be studied in far greater detail. Neptune provides one of the best opportunities to perform that calibration. For example, many exoplanets classified as sub-Neptunes or mini-Neptunes occupy a size range that does not exist among the planets orbiting the Sun. Understanding whether these worlds possess deep, volatile-rich atmospheres, water-rich interiors, or compositions unlike anything found in the solar system requires confidence in the physics used to model high-pressure planetary interiors. Every improvement in our understanding of Neptune's structure feeds directly into those models. A better understanding of heat transport inside Neptune becomes a better understanding of heat transport inside countless exoplanets. A better understanding of atmospheric chemistry on Neptune becomes a better framework for interpreting the spectra of distant worlds. There is also a temporal dimension to Neptune's scientific value. The planet's orbital period around the Sun is approximately 165 Earth years. Since its discovery in 1846, Neptune has completed only a single orbit. Modern planetary science has therefore observed less than one full Neptunian year. Many of the atmospheric changes now being tracked by JWST are occurring on seasonal timescales that human observers are witnessing for the first time. The cooling stratosphere, the changing cloud populations, the shifting brightness patterns near the poles, and the evolution of auroral activity may all be components of seasonal cycles whose full behavior remains unknown simply because humanity has not been observing the planet long enough. This means that every decade of new observations adds information that cannot be recovered later. Missed observations represent permanently lost opportunities to document how a planetary climate system evolves over time. The value of continuous monitoring therefore increases rather than decreases as the observational record grows. The longer the record becomes, the more scientists can distinguish between short-term fluctuations and genuine long-term trends. In this sense, Neptune occupies a unique position in planetary science. It is simultaneously a nearby world, an analogue for countless exoplanets, a relic of solar system formation, and a laboratory for physical processes operating under conditions impossible to reproduce on Earth. Its atmosphere preserves clues about planetary climate. Its magnetic field preserves clues about exotic states of matter deep within its interior. Its rings preserve clues about dynamical evolution. Triton preserves clues about the primordial Kuiper belt. Each component contributes a different chapter to the same larger story. JWST has not completed that story. It has only provided the most detailed glimpse yet into a system that remains far from fully understood. The observations gathered since 2022 have demonstrated that Neptune still contains phenomena that existing theories struggle to explain. Rather than closing questions, the telescope has expanded them. The result is that the outermost major planet in the solar system continues to occupy the same role it has held since its mathematical discovery in the 19th century. A world whose greatest scientific contribution is forcing us to rethink what we thought we already knew. The limits of prediction. The images and spectroscopic data that JWST has returned from Neptune since 2022 have each carried a specific kind of surprise. Rings that had been invisible for 3 decades. An aurora that had been searched for across 4 decades of technology development. An ionosphere that had shed nearly half its thermal energy since Voyager 2 measured it. A stratosphere that cooled during summer. Clouds that vanished and are only slowly returning. A polar brightness that existing models cannot fully explain. The confusion that these findings generate among scientists is not the confusion of a field that has run out of ideas. It is the productive confusion of a field that has just received more information than its existing framework can absorb, and is now engaged in the work of building a better framework. The models will be revised. The revised models will make new predictions. Future observations will test those predictions and probably produce new surprises. This is the cycle by which scientific understanding advances, and Neptune is currently driving it in planetary science at an unusual pace. What makes the situation remarkable is that all of this is happening without a spacecraft at Neptune, without a probe in its atmosphere, without an orbiter mapping its magnetic field or measuring its gravitational harmonics from close range. Everything described in this script was obtained from a distance of 4.5 billion kilometres, using a telescope designed primarily to look at objects billions of light years away, pointed at the edge of our own solar system, and finding there a planet as full of questions as any galaxy it was built to study. Neptune has been waiting at the edge of everything for nearly 200 years of human observation. Each instrument that has finally been capable of seeing it clearly has found something unexpected. JWST is the most capable of all those instruments, and Neptune, true to its pattern, has not disappointed.